Hi, I'm Professor Goins, and in this video I'm going to take a look at the concept of a one-sided derivative. First and foremost, recall that the value of a derivative is the slope of the linear approximation to a graph. For example, let's say I've got this red curve here and I was to pick this point on the graph corresponding to x equal to a. Notice that if I draw a straight line at that's tangent to that point, this is our point of tangency, the slope of this line, again, that's the line that best approximates the graph on both sides of that point, right? So if I was to zoom in, this green line and the red line become indistinguishable as I get closer and closer. That's the idea of a linear approximation. And the slope of that linear approximation, again, is the derivative evaluated at a. Now consider the following graph. Let's look at this red graph here. Same one over there. It's the same function. If I look at the linear slope to the left, or the linear approximation to the left and the linear approximation on the right, they're different at that point x equal to a. So the linear approximation on the left does not equal the linear approximation on the right. Okay? So therefore the derivative doesn't exist because there's not a straight line approximation like we have here that works on both sides. All right, so what we can do is we can just look at the slope from the left and the slope from the right. Slope from the left. What I do is I approximate it with a secant line, right? Same thing we would do when we did the derivative. We approximated the tangent line to the secant line. So I'll approximate the slope from the left using a secant line. Now with that secant line, what I have to do is pick a point on the graph that's to the left of this, point of tangency. And so what I did is I call it a plus h just to be consistent with from the right, but notice that h does have to be negative. So this is a plus h is smaller than a, so h is negative in this case. Well, to get the exact slope at this point from the left, I'm going to take the limit as h goes to 0. And that would again take this point here on the graph, and that would get it closer and closer to this, again, sort of point of tangency from the left. And what I do is I take the limit of the difference quotient as h goes to 0, but in particular when h is negative. That will give me the slope from the left. Similarly, the slope from the right. Well, what I do is, again, I'm going to approximate with a secant line where the point for the secant line, other than this, again, point of tangency from the right, is I'm going to take a point that's to the right of that. Again, I'll label that as a plus h to be consistent, but in this case, h is positive. So what I do is I take the limit of the difference quotient, where h goes to 0, just like the normal derivative, but in particular, h has to be greater than 0. Now remember that if h goes to 0 and h is negative, that means h goes to 0 from the left of 0. This is simply a left-hand limit. This is a right-hand limit. Okay, so with that general concept, let me write the definition of the left and right hand derivative, and then we'll do a couple examples. Okay. Definition. The right-hand derivative of f of x at x equal to a is given by the following. It's equal to the limit of the difference quotient So same thing we have here. And when I take the limit, I take it as h goes to 0 from the left. So h goes to 0 from the left simply means h goes to 0 and h is negative. And the notation for this is, well, it's related to the function f. It's a type of a derivative. It's related to the point a. But since it's coming, from the right, that'd be as h goes to 0 from the positive. So from the right, h goes to 0, h is greater than 0. That means h goes to 0 from the right. It's a right-hand limit. And then from the right, I'm going to put a plus sign here. Similarly, the left-hand derivative of f of x at x equal to a is, so the left-hand derivative, again, it's a limit of the difference quotient evaluated at a. And I do take the limit as h goes to 0. But again, the slope from the left, which is the left-hand derivative, h goes to 0, h is less than 0, so that means h goes to 0 from the left. And again, notation similar to a right-hand derivative. I just put a minus here to indicate that it's a derivative from the left. So there's the definitions for the left and the right-hand derivative. Let's look at a couple functions and compute their left and right-hand derivatives. Let's start with an absolute value function. For example, let's look at the function f of x is equal to the absolute value of x minus 3. So remember that the shape of the absolute value function is the V shape, and it has sort of the vertex at the origin opening upwards. Remember that x minus 3, if I replace x with x minus 3, this would be a horizontal shift to the right of 3 units of that graph. In other words, the graph looks like this. Okay, so just a rough sketch. This would be the absolute value of x minus 3. What I want to do is let's compute the right and left hand derivative at 3. Okay. Solution. For the right hand derivative at 3, let's write out the difference quotient of this. This is the limit as h goes to 0 from the right of f of, so what is a in this case, right? So I'm computing it at 3, so that means that your a value is 3. So when I write out my difference quotient, this would be 3 plus h. So f of 3 plus h minus f of a, so f of 3, and then divided by h. This gives me the limit as h goes to 0 again from the right. F of 3 plus h, that means I'd have the absolute value of 3 plus h minus 3 minus the absolute value of 3 minus 3 over h. Simplifying that, inside the first absolute value, 3 minus 3 cancels, giving me the absolute value of h. 3 minus 3 is 0. The absolute value of 0 is 0. And then the denominator is just h. Okay, so we boil it down to this expression right here. Now, as h goes to 0 from the right, remember that this means that h is positive. If h is positive, then the absolute value of h equals h. Right? If h is 2, the absolute value of positive 2 is 2. Absolute value of 1 is 1. So on and so forth. Therefore, we can rewrite this expression without an absolute value bar, giving me the limit as h goes to 0 from the right of h over h. And of course, h over h is 1. the limit of a constant is that constant, and therefore the limit is 1. That means, conceptually, if I look at this graph, at this point x equal to 3, the slope from the right is 1, and that kind of sort of matches our graph here. The slope here is 1. All right, now let's take a look at the slope from the other side, or the left-hand derivative. Now, for this one, well, let me not get ahead of myself. For this one, again, it's the left-hand derivative of the difference quotient. Now, we could go through and simplify the difference quotient, but notice it's the same expression that I had up here for the right-hand derivative. The only thing that changes between these two computations is when I take the limit as h goes to 0 from the left. And that's going to be the exact same simplification all the way down to this point right here. Remember, the only place that I used where h goes to 0 from the right was to drop the absolute value. So for this one, we can skip a few steps because it's the exact same work as above, and we can just start right here. All right, now remember, h is negative. That means the absolute value of h is the opposite sign of h. If h is negative 2, then the absolute value is positive 2, or in other words, negative 2, which of course is positive 2. So we can rewrite the absolute value of h as negative h. So this is h goes to 0 from the left of negative h over h. And of course, negative h over h is negative 1, so therefore this is negative 1. That means that at the point x equal to 3, if I look at the slope coming from the left-hand side, my slope is negative 1. And again, that matches our graph. Okay, let's take a look at one more example. And I'll leave the definition up there, so I'll erase what I have on the right of the board. But this is a typical example using left and right-hand derivatives for absolute value functions, because it has a what you'll learn in another sections, that's called a corner. So it does have different values on the left and the right. Let's take a look at another typical example. Another typical example is to compute the derivative from the left and the right where you're given a piecewise function. Okay, so, I mean, an absolute value function, of course, is a piecewise function. But this one is going to be written more explicitly as a piecewise. So 2x squared plus 2x minus 3 if, say, x is less than 1. And then let's say I've got... let's see. Actually, let me change this to a 3. And then I'll do 5x minus 7 if x is greater than or equal to 1. Let me think about that just to make sure. Let me change this sign and this sign. Okay, let's compute the right-hand derivative at 1 and the left-hand derivative at 1. So it's going to be the right and left-hand derivative for this piecewise function. Starting with the right-hand derivative, f prime plus at 1, so is the limit as h approaches 0, again from the right, of f of 1 plus h minus f of 1 all over h. So let's think about this for a second. F of 1 plus h, as h goes to 0 from the right. H goes to 0 from the right means h is positive. In particular, h could be 1. That means that I would have 1 plus 1, which is f of 2, or f of 1.5, f of 1.1, something like that, meaning that this input is larger than 1. Well, which function expression do I use when the input is larger than 1? That would be the negative 5x plus 7. All right, so if I go ahead and plug in 1 plus h into this function expression, this gives me negative 5 times 1 plus h plus 7 minus f of 1. If I plug 1 into the function, I get this is this part here includes 1, so therefore I plug it into this, giving me that would be positive 2, so minus 2 all over h. Okay, simplify that numerator. I would get negative 5 minus 5h plus 7 minus 2 all over h. So again, I just distributed the negative 5 through the parentheses. And then notice I would have negative 5 minus 2, so that's negative 7 plus 7. That cancels. So the constants cancel. What's left over, I have negative 5h over h. After I cancel those constants, then I can cancel the h on the top and the bottom, and then I have the limit as h goes to 0 of negative 5, which equals negative 5. Therefore, for this piecewise function, if I look at the graph, at x equal to 1, and then coming from the right, the slope would be negative 5. All right, now let's look at the slope coming from the left. F prime from the left of 1. All right, so this would be a left-hand limit. This gives me the limit. H goes to 0 from the left. F of 1 plus h minus f of 1 all over h. Now, h goes to 0 from the left, means h is negative. If h is negative, then 1 plus h, for example, 1 minus a half would be a half. 1 minus 0.1 would be 0.9. In other words, the inputs are less than 1. Which function expression do I use for inputs less than 1? That would be this top one here. All right, this would give you the following difference quotient. H goes to 0 from the left of, I'm going to take 1 plus h and plug it into this quadratic. I would get 2 times 1 plus h squared plus 3 times 1 plus h minus 3. That right there so far is the quadratic function up here with 1 plus h plugged in. Then minus f of 1. Well, if I plug 1 in, again, I plug it into this expression here, and I get 2. So this would be minus 2, and then all over h. Notice I had to use a different expression here depending on if I was doing a right hand or a left hand limit. So make sure you pay attention to which function expression you need to use. All right, so from here on out, I just have to expand this and then simplify as much as I can. Okay, let's go ahead and do that. I will continue that. I guess we could do it over here. So I'll say equal to dot, dot, dot. So just so I can leave everything up on the board, I'll say dot, 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 and then equals. All right, so I go ahead and I expand that limit, or the difference quotient. I get the limit, h goes to 0 from the left, 1 plus h squared, and then distribute a 2 through that. You would get 2 plus, and then I would have 1 plus h squared to give me a 2h, and then that would be 4h plus h, or 2h squared, plus 3 plus 3h minus 3 minus 2 all over h. So let's see what cancels. Positive 2 minus 2, positive 3 minus 3. Let's rewrite what we have just to clean it up. Limit h goes to 0 from the left. All three terms that remain have an h. So if I factor h out, I would get h. And then I had 4 of them here, 3 of them here. That would give you 7. 2h squared, if I pull an h out, I get a 2h all over h. Now I can cancel a common factor of h on top, h on the bottom. This expression I can plug 0 in, giving me 7 plus 2 times 0, which of course is 7. That means for this piecewise function, if I graphed it, the slope to the right of 1, so as I approach 1 from the right of the graph, the slope would be 7.